Good evening and welcome to NOSP event in Stavanger. Welcome also to the audience that we're broadcasting to. Before we go ahead, I'd just like to go through some safety procedures with you. So the alarm system, if the alarm goes off, we know the procedure that we follow the green guy that is running and the arrows, and we go down to the reception area. We go out, cross the street, and the part on the other side is the muster point for the hotel. Then also because the restrooms are out in the corridor, and the first is to the right. You find them there. Okay. Again, welcome. I also start with a big thanks to our sponsors. I think we are now more than 30 sponsors to NOSP. We very welcome these. This gives us the possibility to have these occasions like this, and also the annual dinner when it comes to November-ish, which we look forward to. As always, we also have the chat room on Discord, so you find the link on nosp.no and click in there, and you can raise questions there, and you can follow discussions. We have probably 6-7 events during the year, and of course we need speakers for these events. So if you have anything that you like to share with the greater audience, broader audience, then we welcome any proposals. Just send them to any of the NOSP board members, and we discuss internally and bring it to you. There are some new events coming up after this. We have first after the summer holiday, and then the big thing in autumn is always the RTS Subsea Innovation Day. It's scheduled for September 1st. Then there will be a Bergen event in October, and as I said, the annual dinner will be in November 17th. Same place as last year. So back to today's, this evening's event. We have 4 presenters. 2 will be here in person, and we have 2 remote. So first out will be Gary Bagot, coming directly from Paris almost, and doing a presentation here. L-Wave. So I think I give the word to you, and you can present yourself and do the presentation. Yeah.
Good evening, everybody. Thank you very much for inviting me to present L-Wave. L-Wave and its technology inspired by nature electric sense, and that we have adapted to really a new technology that we call CEDAR for controlled electric detection and ranging. So L-Wave, it's a small company. We have 15 people, and we are the first company in the world to work on this new technology that we have been working on since now 4 years. Main application are subsea application for obstacle avoidance and buried object detection. It can be buried pipelines, buried cables, UXO, but also mines. And for obstacle avoidance, that's a complementary solution to camera and sonar that we can also place on robotic arms. So Aerowave is a young company founded in 2018, but it's based, I mean, the core of the technology is based on a patent issued from 10 years R&D from a scientific partner, a university in France called IMT Atlantic, especially the biorobotics department of IMT Atlantic, worked during 10 years on this electric sense to replicate what is a sense that we can observe at some fish, some tropical fish. We'll see that after. And now, since 4 years, so Aerowave is adapting the technology to the need of the industry and also the defense. For the defense, for instance, we work on a European Commission project called Miracle for mine warfare, gathered by 25 university and industry leaders, and will be on board an AUV from ECA Robotics to detect buried mines next year. We are also very proud to have been awarded this blue window economy grant from European Commission to develop our sensor that will be launched after summer. And we are already working with several big names of the offshore and the defense. So the technology, if there is one slide to remember tonight, it's really this one. So what is this electric sense? It's a sense that appeared in nature 2 times independently in South America and in Africa to some different fishes. We see one of them here, the elephant nose fish. And those fish, they live in congested environment in a tropical rainforest, mangrove. It's full of leaves, roots, so echolocation is not working. It's turbid, so vision is not efficient. So this little fish is like a battery. You have a positive pole in the tail and negative poles all around the skin, which are the electroreceptors. And the fish permanently emits an electric field. Okay, you see here the line of field going from the tail to the body. And you see here the color code is like a gradient of the amplitude of the signal measured. And the fish kind of memorize this electric image of its environment when there is nothing around it. And when an object is penetrating the detection bubble, a conductive object will focus the line of field, and so we'll have a peak of intensity, a peak of amplitude on the skin. If it's an insulated material object, which is in the bubble, detection bubble, in that case, the line of field will diverge all around the object, spreading over a larger area of the body, and so the intensity is decreasing. So what the fish observe is some intensity modulation of its own signal. So that's for the amplitude, but also the fish can look to the phase shift of the signal and detect if it's an alive object or not, because living cells are capacitive, so that phase the signal, and so he can see if it's another fish, if it's an alga or whatever. So all this principle, that's what we try to replicate at Aerowave. Okay. So about the architecture of the product, how we are going to deploy it. So you have, I will show you the hardwares and the softwares or the algorithm that can do different things with the same hardwares. Okay. In terms of hardwares, so we have a first version, a 300 meter depth rating system that's going to be launched after summer. It's made of a pod with all the electronic and real-time processing of the signal, and some electrodes, up to 8 electrodes. You see that the systems are quite compact and light, and it's really modular. You can put between 2 and 8 electrodes, depending what you want to do. So here you have 3 connectors for serial, Ethernet, and external sensor connection. Part of the important external sensor are conductivity temperature probe, because we compensate from variation of the environment, obviously. What we want to see is a variation of our signal due to a new object not due to a change of the seawater salinity, for instance. And on the other side, you have 8 also subcon connector to connect to your plug to your electrodes. Just a little bit later, we're going to launch also a 6,000 meter version. It's exactly the same electronic inside. We just changed the titanium housing and the connectors. And here you don't have 8 plugs, but 2 big plugs to connect 2 octopus, so 2 times 8 electrodes, up to 8 electrodes to your hardware. Software modules. The first one is what we call the safety shield. I was mentioning that it could be a complementary solution to your sonar or to your obstacle avoidance sonar. The sonar is directional, camera is directional. Sonar has a longer range than us, and the camera more resolution, but we can provide omnidirectional, we make the bubble and like the fish. So we provide an omnidirectional and instantaneous detection of the environment, of the closed environment. Just to give you an idea of the detection range, it depends on the spacing between the electrodes. Okay, so if I'm on an AUV of 5 meters long, the radius of the detection bubble in the water is 25 meters. And this detection range will tend to reduce a little bit when it's inside the marine sediment. When you go closer to the seabed, you will see what is inside the seabed. But the main limitation of the system, the technology, is the detection range. We have designed the product to be compact, to be low power consumption. And so you have no perfect sensor, it's just a compromise. But still, you have quite some good opportunities to see the added value. It's a bit like your backup camera on a car. 20 years ago, it was not existing. Nobody cares. Now everybody is happy to have that on a car. Maybe one day the ROV pilot operating close to manifold or Christmas tree will be happy to have this in addition to their camera and their sonar. And you see here a small video on the back of a test. It's quite an old test, but it's 2 years ago for simulate a weather inspection, for instance. 2 other modules. So all those modules are software with algorithm in the background. Algorithms are in the pod, in the bottle, running in real time. And after you have software on your own PC that when you can visualize, you can configure your software and you can visualize the data. One software will be deployed at first for UXO. Basically, we'll do a resistivity chart. It's like a waterfall image from a side scan. It will be the same principle, but a resistivity chart. And so you will be able to see insulated and conductive objects appearing on the chart. There is no, if you compare that to magnetometers, they can only see ferrous target. We don't care about the ferrous equivalent. We see any target which has a conductivity different than the environment. So for us, the only object we will not see is an object which has the same conductivity as a marine sediment and the sand, if it's in the sand, or if it has the same conductivity as the water, if it's in the water. That will be transparency. Otherwise, we'll see a gradient of color. We'll have then an upgrade of this module. This will be UXO 2D. We'll have an upgrade called UXO 3D. If people want to have the size and shape and depth of burial of the object, it will be possible. For the shape, it will be approximative. We develop some models of the electric response of a sphere, of a cylinder, of an ellipsoid, of a plane. In that case, it will be helpful to identify what type of mine, what type of UXO is inside, and also will give the conductivity. So for buried object identification, that will be very helpful. Also for pipe tracking. Pipe and cable tracking, you see here how it will be fitted. So it will be here just a simple skid that you can just plug to your ROV. No need anymore to have a big frame in front of your ROV that you need to remove if you want to use your arm. Here it's a skid where that you can have a small skid for observation class ROV or big skid for work class ROV. Here the electrodes are all looking down, constraining the field to go to the marine sediment. So it's very compact, very light. And the good added value is also that you will be able to track an active power cable. So if you're on a wind farm, today with the existing system, you need to switch off the production of the wind farm to be able to see the cable. Here, we'll be able to track anything because the system is designed, it has certain bandwidths. It listens to the noise of the environment. It can be from the ROV, or it can be from the noise coming from the power cable. And we restrict our working bandwidth to something less noisy, and we filter the remaining noise. And then in terms of visualization, here it will be a simple lateral offset of your pipeline or cable and logging the depth of burial. And so that's something that when you have an ROV, for instance, you can see in real time, but you can also log the data from an IUV and plan also in real time automated tracking of your buried pipeline, of your buried cable. Here are some examples of detection capabilities. So I told you we can see anything which has a different conductivity than the surrounding environment. Obviously, the more difference we have in conductivity with the environment, the easier it is to see. So it's easier to see a big object in metal than a small object in plastic, obviously. So that's why, for instance, for us, our signal do not penetrate the object. Just the object is or helping or slowing the signal. So, for example, this type of fiber optic cable here is for us perceived as a purely insulated material. We don't care about the copper inside, so it's difficult to see. That's why you probably need to have quite a big vehicle to go quite close to the seabed to be able to catch it when it's buried. But then for a big pipeline, it's much more easier. Here it's very constraintful. This type of cable, you have plenty umbilicals or even communication cable which are bigger. Here I really take the most constraintful. Something very interesting for offshore survey, for UXO survey, for the wind farm. Today, the magnetometer, they struggle to find these LMBs from the World War II, this German mine, because it's non-ferrous or almost non-ferrous. For us, we don't care. For us, it's just a big object which is conductive, so it's easy to catch, like the LMA, and we can also see the modern mines like the Manta. It's not finished, actually. I present you the technology and the first algorithm we have developed and we will launch on the market. There are further applications of the technology with the same sensor, with the same hardware. It will be just new firmware that will be able to upgrade your system, knowing that you can have several software running at the same time. Okay, it's not one or the other. It's together. It can work. The system will manage to trigger all the electrodes around the vehicle or just the electrode looking down, and etc. One potential of the technology that we will work on is structural inspection to find cracks on the pipeline coating. If you have a crack on the coating, which is insulated material that let appear the steel part of the pipe, obviously we have a peak of intensity. Biofouling, I told you it will shift the phase of the signal. That's something we want to evaluate also, to be able to assess the quantity per square meter, I would say, of the structure, the quantity of biofouling, and so the mechanical constraint on the structure. There will be also cathodic protection monitoring. If we turn off in passive mode, we can listen to any noise in the water, because the electronic inside is very accurate. Well, that's a potential. The second one we are working on, and here we have some good discussion with a very famous university from Norway that we will not mention now, but we send a complex signal in the water, several frequencies. Each metal has a different conductivity. That means that each metal will give a different answer to a different response to our signal. And what we want to bring for deep sea mineral is identification of the minerals in the sediment, saying this is more copper, this is more cobalt, and so on, and without contact from an IUV. So that to reduce the need of sending an ROV to grab samples and to be analyzed. And also, as I told you, with the phase shift observation, the idea is also to detect the life, because it's the second objective of deep sea mineral exploration, is also to find the metals, but also to see if the area is an habitat for the life. Voilà, and to finish this presentation, say let's go subsea. So after summer, we are going to start some demo, and so we'll be happy to do that with our friend here from Go Subsea, and to help you to see the performance of our system for cable laying, buried cable, buried pipelines, or UXO applications. Voilà, that's it for me.
Thank you.
Yeah, thanks, Gary, for that. Any questions?
Is there any available systems as of now?
Not yet, because today we have basically we have worked since 4 years on a prototype. This prototype was not sensitive enough for buried object. It was good performance for in the water for obstacle avoidance, but for buried object, it's more complicated, you need more sensitivity. So it has been a bit a challenge to find all the good electronic components at this time. We procured all of them to build some system, and we are conducting now qualification of the system internally, and we are fully booked already September to November to do some demo with the new system, but the new system has never been in the hand of the client for now.
Okay. But you are planning to commercialize it, so so it will be able for a lot of players, or?
You mean, sorry?
No, will it be available for everyone? So
Yeah, we just sell
selling
the product.
equipment.
Yeah,
Yes,
we
it's not a
don't do
service.
service, we don't operate it.
Okay.
It's really plug and play, and don't intervene.
No, that's great. Interesting.
Thank you.
Could you say something about, sorry,
Go ahead.
the data set, or what sort of data set you collect? Is it you, the documentation and the output from that? Is
Yeah,
that
so
cloud, or
if you go for UXO, for instance, so I mentioned the UXO 2D, the resistivity map. So here you will be able to output simply an ASCII file that you can upload to Oasis Montage or other UXO visualization software. And for UXO 3D, in addition, we output also a simple log file with the position, time, depth of the area, conductivity, shape, and size of the UXO detected. For pipe and cable tracking, it will be a very, very standard protocol in the industry that you can also include into any navigation package.
For the UXO part, do you expect to have like 25 meters range?
No.
No.
No, 25 meters is really for a vehicle of 5 meters long in the water column. The factor of detection is 5 times the spacing between the electrodes in the water. When this bubble touch the marine sediment, the marine sediment are less conductive than the water, so you see less. Okay. So for the detection capability, depends how close you are, depends the size of your vehicle, the nature of the object. That's why we do a lot of simulation. That we work already with some people to tell them with our sensor on their vehicle what they can see, what they cannot see. It's really exponential.
you can deliver 50% of the promise, it's a small revolution.
Derek, have you questions?
A couple of questions. Survey speed. Do you
No,
see your system
It's
as
not a
limited?
limitation
Not a
because
limitation.
we have an acquisition of which is very high actually. So what happens on the electrodes? They can be positive, negative, or disconnected. we swap the status extremely fast, and we do the acquisition at 3 MHz. 3 MHz. So it's for the speed you don't care at all. Now, really, the only limitation of the system is the range. With the design we have here, you will never see something, even if we go very close on the big vehicles, you will never see something, even a big object at more than 5 meter depth of barrier. But I think it can already do some job.
And this is maybe a stupid question, but we're used when we're dealing with the conventional bike trackers to target scaling tests with products up front, background compensations. Are we going to see the end of that? So, normally, if we're laying a pipe and entrenching it, we would cut the section out, send it to the pipe tracker supplier, and then they would get a scaling factor for the system. But that's not something we require? We will learn. I think it's not totally finalized now. As I told you, we have a new high sensitivity electronic. We need to go assi. We need to do some demo. We need to have some feedback. I cannot answer to you. We have tried to be as much as possible self-compensated, that we can adapt to any target. But after, again, nothing is perfect, but we try to do our best. I think that Cygnus has the speed in itself is a small revolution.
Yeah, and the maneuverability and the fact that you don't have to bring the ROV back from deck to retrieve the big pipe tracker, and you can jump from pipe tracking to another application.
Okay, thank you, Gary. A small gift from NOSP for your.
Oh, thank you very much.
Just to people that present here, we open the bar after the next presentation, so don't be hysterical about your drinking here. More to come. Yeah. The next presenter is Rick Lear from Astra Marine, and I think we have you are here now, Rick. Can you hear us?
Yes, I can hear you. Can you hear me okay?
We can hear you very well. I think I leave the stage to you then, and you can present yourself and your products.
Okay. Well, evening, everyone. Thank you very much for the invitation. I left the Royal Air Force in 1991 and bounced around the North Sea for a little while as a ROV pilot and surveyor before joining Rison in 1992. And I stayed with Rison for 20 years, mostly in research and development, but also in project and product management. In 2012, I had a change and I went to DOF, and I spent almost 10 years with DOF as a senior surveyor and doing a lot of the internal and external training. When all this COVID stuff kicked off, it part, and I left DOF and I started a little company called Astra Marine. I'm now semi-retired. I spend most of my time sailing when the weather's nice. But I do occasional, what I call interesting projects. And this is one I'd like to show you this evening. It's a little bit different than probably the main core of offshore stuff, but I hope you'll find it interesting. Can you see that that screen okay?
I'm not sure if it's coming, Rich. Are you sharing your second screen with us?
I knew there was something I needed to do. Just hang on 2 seconds. Share screen. All right, we'll try that again.
There we go. It's coming now.
Okay, good. All right, now I'll just get the pointer up here. Okay, so this, as I say, a little bit different than normal offshore stuff, but it was a multi-sensor inland survey that was conducted end of last year with 4 different companies. Viewport 3, who Some of you will know from the offshore photogrammetry type world, they did the main project management for this contract. Astromarine, that's me. I did the multi-beam and the LiDAR surveys, the data management and the reporting. Below and Beyond, they're a UK-based ROV company. They did all the ROV work, and Leaping Wing did all the UAV surveys and the photogrammetry data processing. So a fair spread of companies and a fair spread of capabilities there. The survey area was quite interesting. It's a flooded quarry in the southwest of the UK. I'm afraid I can't tell you much more than that. But when quarrying stopped there, it was flooded deliberately and was turned into a recreational dive centre. So the area itself is about 600 meters long by about 150 meters wide at its widest point. And the water depth goes from nothing up here where there's a slipway, and you can see it just here in this bottom image, right down to about 80 meters in its deepest point. And it's used for recreational diver training, so scuba diver training, but also a lot by the police and military authorities to conduct exercises and so on. These green objects you can see here are Zipline Tower. So there's a huge zip line that goes from up on the top here right down to these towers. And all this here is, well, it's sort of a floating, bouncy castle type stuff. And people could come along and have fun in the nice weather and do all the recreational stuff there. The interesting thing about this area is it has a whole bunch of targets in it. There's about 32, I think, altogether, and a number of military vehicles, helicopters, aircraft, boats, buses, mines, and then all sorts of work platforms and other stuff that's kicking around. This area over here is the shallow area, so you can see the main majority of the targets are in the shallow area. But also this area down here is around the 80 meters point. Nothing much down there, but there's some targets here in 60, 70 meters of water. So quite a variety of targets. The purpose of this survey was to collect data primarily to accurately map the entire site for development work. The site was being sold and developed. And up until then, all they had is a sort of fairly coarse bathymetry over a small part of the area. And so they wanted to accurately map the site, mainly to confirm all the targets are in place and to accurately plot the locations of each of these targets. And then on top of that, to get as much detailed subsea topography as possible so they could work on their plans for development. So the equipment that was used was an orbit multi-beam, the Wbms system, a UAV with a camera, an ROV with normal cameras, and the Norbit LiDAR system that went along with the multi-beam. We mounted all the subsea equipment on a nice survey boat that we brought into the site specifically for this job. I don't know if you can see here, but this is the Norbit, what they call the Portus Pole, which is a carbon fiber pole that holds both the multi-beam, the LiDAR, and the antenna. So you can see the antennas here. The pole's swung forward here for deployment, but the two antennas, there's the main part of the pole, the multi-beam on the end, and you can just maybe see the LiDAR that's sitting there. We went with this arrangement specifically because, of course, a rib like this isn't very rigid, so we had to have a multi-beam with the motion sensor integrated into the bottom end and take out as much of the uncertainty that's involved with mounting this stuff onto a boat as possible. We set up a number of control points before we started the surveys. because one of the challenges is we had to try and tie in the UAV data along with the LiDAR and then the multi-beam data. I don't know if any of you are familiar with these things. These are very clever. These are called Aero GNSS points. So essentially there's a little solar panel and there's a GNSS receiver. So all you do is lay these out on a site. They record data using a Wi-Fi based reference system, so you get RTK sort of accuracies. And then they all communicate with each other and back to a central controlling laptop via Wi-Fi. So they're very easy to set up and operate. You know, the traditional way, of course, is tripods and GPS and all that sort of stuff. But these things, you just go throw them out. They can be seen from the air by the UAV, where we could see some of them with the LiDAR, which is what we needed to tie everything together. So that was time well spent setting up these control points. The ROV crew, what we did is we carried out the survey first. We picked targets and then the ROV dived on them. And here's an example of some of the targets. I hope you can see those. So you can see that they vary from sort of big aircraft. Some of you will recognize a Land Rover there, the nose of a helicopter. These are sort of military vehicles, a couple of boats, and one of the mines that are used for the military type training. So we did the surveys over a couple of days. So we set up the control points, mobilized the multi-beam, and while we were doing that, the ROV guys were working in the shallow water areas. And then on the second day, we carried out all the main surveys. Two main issues we found. This was my line plan. This is what we actually did. and the reason for that is that there were a lot of obstructions in the water that we weren't aware of. A lot of floating lines, a lot of debris right below the surface, and it was really quite difficult to operate around it. And so that was something of a challenge. The other issue was the weather. This was taken on the day of the surveys, and you might look at that and think, well, there's nothing wrong with that weather. And no, there isn't, unless you're trying to fly in a UAV and get photogrammetry. And this mist persisted for 2 or 3 days, unfortunately, which made it difficult. But having said that, we got our data, and of course that's the aim of the game here. So the data flow. So we had the multi-beam set up along with the LiDAR, and because the multi-beam has an integrated position and attitude system, that means the multi-beam data is co-located with the LiDAR data because it's all from the same reference point, or the rest of the same source. We used software called CUDA-Core, and you may not have heard of CUDA-Core before, but it's a new IVA piece of software that really combines Navipack and Naviscan into one package. So that was used for data acquisition, Navi-Edit, Navi-Model, and then output an XYZ. The UAV side of things, so the UAV collects photogrammetry. It has position and attitude information, and then Agisoft Metashape was used to extract photogrammetry points in LAS format, which is essentially an XYZ type of format. Cloud Compare was used for processing the majority of the data. Cloud Compare is freeware. It's very good. The great thing with Cloud Compare is there's lots of geeks that sit around all over the world somewhere, and if you just send a message on a forum to say, hey, does anyone know how to do this, or can anyone help you with this, you know, someone is sitting there and will answer you, and people write modules for it all the time. So it's actually a great open source piece of software that's very useful. The deliverables were quite straightforward. A narrative report, as you might expect, as you're used to seeing offshore. All the data was digital, so no CAD charts or anything like that, all digital data. And then the video and images from the ROV. So the The data set looks like this. So there's the multi-beam data in the middle with the photogrammetry from the UAV all around it. The UAV collected around a billion points. And then when you add in 55 odd million from the multi-beam and another 55 million from the LiDAR, you soon start to realize that the biggest challenge here is just the volume of data, nothing else. If we look at some of the multi-beam data, this target you can see here is the BAE 146, which is a regional airliner. They're mostly out of service now, but you can sort of judge the size of it there. That's what it looks like on the multi-beam. And when you start looking at the resolution, in 30 meters of depth, we're seeing around 5 centimeters or so point spacing. And that was by multiple lines over the target. But that sort of order of point spacing is what we saw. The LiDAR, well, you can judge it by yourself. This is the ROV guys, one of them sitting down looking at YouTube or something on his phone while the other one's working. But at the same sort of distance, at between 10 to 40 meters, the point spacing is around a centimeter. Now, we didn't actually deliver the LiDAR data. All we used that for is to tie in the subsurface and the surface data sets, because we needed to be able to see common points in two data sets in order to merge them. And because the LiDAR uses the same navigation and attitude source as the multi-beam, we were able to tie those in quite nicely. If we look now at the photogrammetry data resolution, well, the UAV collected around 10,000 images at 2-second intervals. It has this very expensive 45 megapixel camera, and typically was operated at an altitude of 40 to 70 meters, depending on what they were looking for. The software was Agisoft Metashape, and that essentially extracts points from the images. And as I mentioned earlier, 1 billion points and point spacing a few millimeters. And I'll try and give you an idea of that. So this is an example of the photogrammetry. This is us mobilizing the boat. But you start to see here that you get this, this photograph type image with points extracted from that. And it really is an excellent, excellent piece of kit. So as you can imagine, with a project like this, there were some challenges and some upsides. So the challenges, we found out only just by chance that the water level in this quarry changes. There's an underground stream, and about 2 days after rainfall, the water changes. And that caused some consternation when we couldn't tie depths in together, but once we found out what was going on, we were able to sort that. As I mentioned earlier, the volume of data is definitely the biggest issue with this this type of survey. Just manipulating 1 billion points on a computer is not easy. Yeah, trying to merge those 3 data sets together took time. And the way we did it in the end, we chopped it up into small chunks and used matching of small chunks, and then applied that to all the data, and then sort of tweaked it from there. Yeah, we had a little bit of an issue. We originally collected all the data in Dead Reaches 84, which was what the client wanted. He then decided that he wanted it all in OSGB 36, which, okay, that's fine. Technically that's not a challenge. However, doing it with 1.1 billion points is a challenge, and that just took a lot of time and a lot of number crunching to shift all that data into a different geodesy. On the upsides, well, having those common points between the multi-beam the UAV and the LiDAR data really eased that merging. It meant that I could quite simply move data sets as I needed them to match them. The other upside was that the deliverables were quite simple. So really it was a digital data output and a written report, and that was about it. And the visibility was excellent. The ROV was able to get good images of all the targets, and it really made life easier that they were able to find those and operate around those easily. And we had great teamwork. It was a good team that operated, and we all worked together well and got it all done. Okay, now I'm going to challenge the bounds of technical possibilities here and try and show you some of the data. Can you see that viewer okay now? Well, okay, I hope you can see it. I'll try not to move this around too much because it's a little bit jerky. So these areas you can see here, these are the floating pontoons around the west side of the area. So the multi-beam is the colored area here, of course, and you can see here from the shallow points, this is about 2 or 3 meters depth here, right down to the deepest point, 80 meters. I just wanted to show you a little bit about this photogrammetry, and if I just zoom into a target here, so if we just look at that container, that is made up of multiple UAV images, and as the viewer starts to build up the points here, you'll start to see that the match between these multiple data sets is exceptionally good. Really very, very little distortion at all. I noticed something when I was looking at this afternoon. If I can show you here. But we missed this in our QC, and I just saw it this afternoon, that there's just need to let this this image build a little bit. So I hope you can see these are some cars parked in a car park, and over 2 separate days, of course, the people park their cars in slightly different places. And I notice over here we've got we've got 2 cars, one at 90 degrees to each other, because someone parked their car in the same spot. One day they parked it facing in, the next day they parked it facing at 90 degrees. And yeah, but it matches very well. You can see there those 2. That's where the 2 trucks were parked in different places on 2 different days. And again, that car parked in 2 different places. And you see that the targets that's stationary, the boat, matches very well. But this was just where the car was parked, and you see how it's 90 degrees out there. Okay, gents, ladies, that's about it. Does anyone have any questions?
Yes, thank you, Rick. Any questions from the audience?
I have a question regarding the point cloud. You work in the point cloud. It's a lot of data, but why work with point clouds? Or why did you not calculate the data? Would that make it a little bit easier?
Yes, it would have been, and we did actually. What I did is once I cleaned the point clouds, then we did export grid data from that. But the client did want full resolution data, so we used a grid to point out specific objects or specific things we wanted to highlight. But yeah, the entire data set was delivered.
I have a question here as well. Did you have any GPS dropout problems when working close to the query walls?
Yes, and that was definitely an issue, which was one of the reasons that we went for the something like the IWBMS with a integrated POSNV essentially, so we could cope with dropouts, because that was identified quite early on as being a potential issue, and the data was post-processed using POSPAC. And so we managed to avoid any problems. Yes, in real time, we were definitely seeing GPS dropouts around the query walls. Yeah.
Okay, I think say thank you to you, Rick. We should actually give you a gift, but difficult across the here, so
Yeah.
we take it next time we see you.
Okay, perfect. Thank you very much.
Thank you.
Thank you.
We will have a 10-minute break, and the bar is again open, so you can fill up your glasses. Okay. Okay, welcome back. Then we are ready to kick off the second part of the evening. And again, I will just say thank you to all the sponsors. Upcoming now is Trevor Pugh from UTech. Trevor is actually retired from UTech, but I had the pleasure to work with him for 5 good years. So, Trevor, can you hear us?
I can hear you. I've shared screen. Can you see my screen?
Not yet, but we're...
I'll stop sharing and share again.
No, I think we are very close now. I think just add it to the screen here, then we are. So I leave it to you, Trevor, then to present yourself and talk about the canopus.
I'll just wait for the screen to share with you. Somebody tell me whether they can see my screen.
It's coming in a second. Just a second, Trevor. It's not on your end. It's on our end. Yeah.
Okay, I'll wait.
There we go. Thank you.
There we go. Good. Right, so managing the risks of being a first user of a positioning system on a construction project is the topic. So I'm Trevor Pugh, as Odd said, representing UTech. So my career goes back to the very early 80s after a degree at Imperial. In geology, geophysics, went to Gardline doing shallow marine geophysical surveys, then moved to Fugro and got into construction support, and then to Technip, which in those days was called Stenner Offshore, and got into pipe lay, trenching, subsea installation, always with a survey slant, and then returning to more pure survey and joining UTech, to focusing then on sort of new technologies and bringing those into UTech and to the market, and also focusing on knowledge transfer within the UTech and the wider Actian group. So UTech's part of Actian, which is puts together multiple subsea companies. So we're in a segment called Geo Services, which has Benthic, Terrasonde, and UTech. Terrasonde mainly in the States. And then there's other companies like Intermore and Aquatic that you might be more familiar with. And everything's about remote access, digital delivery, working with other companies, and getting some technology out there. So this isn't a talk about a new piece of equipment or some new technology. It's about the process of being a first user of a new piece of equipment or some new technology and making sure that it works. Because if it doesn't work, then it's going to cost a lot of money, it's going to have a lot of reputational damage, which can lead to a loss of future work. And then for the manufacturer of the new equipment, then if they get a bad track record, it can delay, if not bury, their new product. So it's a very risky, and you have to make sure it's going to work properly. So the new technology that we wanted to adopt was the Canopus Ramses Sparse LBL from X-Blue. This is a range-aided INS positioning system, which means you can use fewer transponders, they've got long battery life, you can use SLAM techniques for the boxing, and they're this interesting shade of pink, just to differentiate them from their competitors. Right, so if you want more details about Canopus and Ramses, then contact Odd, all go to Xblue direct. Now, the reason we chose it to show to our clients, right, because it's going to bring cost savings to our clients, and we also wanted an alternative to the established suppliers and also to conventional LBL positioning. We wanted to try out sparse LBL. But this wasn't going to be a trial or a demo. Right? The Xblue kit has been around for several years, and it's been lots of trials, lots of demos. Right? This was going to be a first use, right? So that you would get the benefits of the cost savings. Now, the first user, as I said, is a very risky. What happens if it doesn't work properly? So we did a risk assessment with Xblue and UTech to identify everything that could go wrong. And we were looking for that probability of a freak combination of circumstances, because the severity was always going to be high. This could lose us a lot of money and a lot of reputation. So it was very important. We couldn't reduce the severity, but we could take the probability down to a freak combination. And that risk assessment was very closely scrutinized by senior management within UTech and within Xblue, because so much was going to be riding on it. So we'll go through a series of the risks and our mitigations that allowed us to use the equipment successfully on the job. Were there going to be enough units ready for the mobilization date? So we did set a delivery date, and which would allow us, if they weren't ready, to just go back to a conventional LBL solution. And then we had sort of fortnightly meetings to monitor production and also to finalize the quantities. And of course, the quantities went up, and Xblue had to sort of gulp a little bit and make sure that they were going to produce the required numbers on time, because they had other commitments as well. So it wasn't just all about UTech. But we managed good communication between us and Xblue, and we got the units that we want, the number of units in the required time. So what happens if Cannabis and Ramses weren't able to meet the requirements for the project? This was a typical deep water installation project, manifolds, flow lines, jumpers, a bit of metrology in there. Right, so we worked through the project with Xblue, defining this is what we would want the Canopus and Ramses to do. Canopus are the transponders, Ramses is the control unit. So Canopus is like a compat, Ramses is like a ROVNAP. So Xblue had to just change the priorities of their development program so that we'd be able to do what we wanted to do on the project. And then, of course, they had to prove it to us. It's no good sort of saying, yep, done that. So this was where they went offshore down at La Ciotat in the south of France to prove that the units could do what we wanted them to do. Now, this was at the height of COVID, so it was very difficult to get anybody to the boat. So what they did was live streamed the trials, cameras, computer displays, the whole piece, with two-way comms to everybody. So it was as if we were there. We were actually able to get one person. One of our offshore surveyors lived in Switzerland and was able to get to the south of France to actually be on the boat. And a lot more about that interaction shortly. So we had to prove that we could do the job. That was done successfully. Then we got on to, yes, but our people are going to have to operate the equipment. Right, so the first step was to get some units across to Aberdeen for our workshop and some of our offshore staff, just to plug them together, see how they look like, get some hands-on experience. So XBlue provided technical support coming round to our workshop, again, during COVID, to just assist with that. And then we also did training courses for the field staff. Again, through COVID, that meant everyone, all the surveyors were sat at home on their laptops or whatever, doing the training course, which had some problems. Right? And we continued this presence, right? So it was of familiarization and hands-on use by being able to operate Canopus and Ramses via the remote link in their test boat off La Ciotat. Right now, for the actual job, then we also took along an XBlue tech, right, for the start of the project, just to make sure, to help our guys and make sure our guys knew what they were doing. But then also, very importantly, and not easy, we established a remote control link between XBlue Office and the offshore spread. So the experts sitting in XBlue's office could actually control the Canopus and Ramses units that were on the boat miles off the coast of East Africa. Now this risk was, we've trained the field crew, but the Canopus Ramses, the software just isn't efficient. And therefore at 3 o'clock in the morning, field staff are struggling to make something happen efficiently. Now this was good feedback from the training. So we were putting all the field staff that were going on the job, went on the training course. And rather than just sitting passively receiving the training, they were sort of going, that's not very good, that didn't work, why doesn't it do it that way? And XBlue weren't sort of going, tough, you get what you get. It was a case of, oh, that's a good idea. We'll modify the software, the user interface, to take your comments into mind. Now that wasn't just done, randomly. It was a controlled process. You were playing with the software. So they not only you were changing the software. So not only did they capture it through their sort of quality system, then it also took the system back offshore at La Ciotat in the south of France and demonstrated that the software changes had been done to the requirements of the field staff. That was a vital step. Again, I'll come back to. So in our risk assessment, we were coming up with these are new equipment. They haven't got the track record. They haven't got the exposure. What happens if the design is flawed and they all flood or they all stop working, some power supply problem? Now, XBlue have a long track record of making sealed housings and transducers and using battery packs. But we did go and audit their design and testing process for the transponders and the Ramses to satisfy ourselves that there'd been a rigorous design and testing process for these units. Similarly, what happens if the manufacturing process was going to be flawed? And so they are nipping some O-ring or something like that so that they flood. So again, we went and did an audit of the manufacturing and testing process. This had to be done remotely, but we were able to, with the XBlue QA system being online, then the auditors, which included myself, were able to see the test process. We could drill down, who did that test, when was it done, what were the results, show me the results of every step of the way. So we could see that there was a very rigorous process for each transponder, each Ramses, convincing us that at each step of the manufacturing process, components had been tested and proved to be functional. But even so, we still took extra spare units offshore above and beyond normal level of spares, because we didn't want the risk of failures leaving us short of equipment. So there were some secondary lessons. Remote training is not as good as in-person training. People were struggling with their laptops being on different formats, different screen resolutions, and so on. And also there was less interaction between the trainer and the trainees, and also less interaction between the trainees during the coffee breaks and everything. So instead of people being able to say, did you understand that last bit? Shall let's ask them to do it again. They just sort of obviously in their own homes, and less interaction. Right, so that's, hopefully we're past that now and we'll be able to get back to in-person training, but just a lesson learned that remote training isn't as good as in-person. Right, field staff need that hands-on familiarization with the hardware and the software. Right, you can't do it all from a book. You need to be actually operating the software. Now, another lesson, you can do quality audits remotely, right? Especially when the quality system is all electronic. Right? Remote control, it's not something that you just turn up and plug and play. There's all the firewalls and security issues, and you've got to engage between multiple IT departments to get remote control. But once it's working, then although we didn't down man on this particular project, I think we proved to ourselves and to XBlue and to the client that remote control permits the down manning on future projects. The biggest lesson, and it's a huge lesson, is you've got to involve the field staff early and extensively. You've got to listen to them, not tell them. If the field staff aren't comfortable with this equipment, then it's just not going to get used, and it or won't be used properly. And they'll find, quite rightly, sort of saying, you know, we don't know what we're doing here. So from the very start, well, not the very start, from very early in this project, the field staff were involved with and made aware, this is what we're planning to do, and this is how we're controlling the risks, and this is what we'll do in training and familiarization with you. So they went offshore knowing that they were going to have an expert with them, knowing they were going to have their remote link, knowing that they'd been through training, and we'd timed the training so that it wasn't too far in advance and they'd forgotten everything. They'd also seen the system and actually had hands-on experience of the system from like last Ciotta tests before they went offshore. Now, that's the biggest lesson, involve the field staff. And that's not just for this XBlue technology. I would say that that applies to taking any new technology offshore. Right? It's not going to happen unless you've got the field staff working with you. Now, there's other things that we learned. It needs commitment. Right? You know, UTech took on additional cost and risk. The supplier had to deliver a working product in enough quantities, right? And both sides have to trust. Right? So, you know, we had to show XBlue all the measures we were putting in place, the training and so on, to convince them that the first job was going to be a success. We had to satisfy ourselves that XBlue were making good equipment and would deliver it on time. So that needs that collaboration and trust. Right? It's a big leap for first use from demos and trials where you've got sort of backup systems. And in that involvement of the field staff, I'll come back to that, it's not just talking about the UTech surveyors, right? You're also talking about the ROV guys and indeed the client project surveyor and the client offshore management. Right? If they're not committed to using this new equipment, then it's not going to happen. So it's getting the field staff, everybody on the boat involved is vital. Now, the risk assessment process that we ran was very good for identifying and managing the risks of the first use. And by sharing that risk assessment, then it gave this sort of collective responsibility. People could see what was being done and go, yeah, that's enough. I'm happy with that. And what came out of that? Well, it worked. We successfully did a couple of hundred of sparse positioning with multiple manifold sites in a remote location. And in doing that, we built up a good pool of knowledge and experience, right, so that we can now offer it to clients. It's not always going to be the best solution, but at least we can talk knowledgeably about the pros and cons of different systems and different techniques. And we also identified in those lessons learned, this risk assessment process, how best to introduce other new systems. Right? And hopefully XBlue will win work now on the back of our experience. They'll be able to cite a successful project. So thank you for listening. Anyone got any questions?
Thank you, Trevor. Yeah, I think there are some questions here, isn't it?
Good question here. The systems you mentioned, the Pontoons and the Gnss, is that correct?
Yeah.
Gnss, are they, let's say, built in-house, or are they available in the market?
Yeah, so these are designed and built by XBlue, French company, I'm sure you all know. And so for this first project, we actually rented them from XBlue. But now these units have been transferred into the rental market. So SDR have some Canopus and Ramses, and Seatronics have more. And Seatronics and RTS have a bit of a tie-up. So if you wanted Canopus and Ramses in Norway, then I suppose your first point would be RTS. But you could also go to Seatronics. So yeah, they are in the rental market. These are the ones that we were using on the project, but there are more being built by XBlue, so there won't be a shortage.
Yeah, Gary?
Yeah, Trevor, a question. Is there a project for UTech to use a Canopus system?
No, not at the moment, because in parallel with our use of Canopus and Ramses, we're also using Fusion 2 and compacts with wideband 2 plus on another project out in the Far East. So you need a certain size of project to make it worthwhile for sparse. Sparse isn't the best solution for every LBL or every INS project. So you have to take your time. Now, in fact, we identified several years ago, we did a huge LBL project, Moho, down in West Africa. Now, a couple of hundred compacts. And at that time, we identified that a sparse solution would have been huge cost savings, but we had to wait a few years before this project came along that we could take those savings of using sparse. So who knows when the next project will come up. There's a few projects that are in the pipeline now for sparse positioning. Whether we do that with Sonodyne or XBlue depends. on commercial and technical issues.
Yeah. Yeah, Derek.
Trevor, can you make any further comparison of Fusion 2 against Canopus, or is that another presentation?
Oh, that would be another presentation. This one is about the process of first user rather than techie stuff.
Right, thank you.
Yeah. We have one for
Had
the
to
autumn.
ask.
Yeah. Excellent. And then I think that's all for now. Thank you, Trevor. I will bring a gift over to you next time in Aberdeen and see if we can hand it over to you. Thank you very much. Then we have one more to go, and that will be Tom Broomfield from Norbit. Welcome. You also came across from Aberdeen, and look forward to your presentation.
Okay. Perfect. Okay. Good evening, everyone. My name's Tom Broomfield, and I'm going to give you a little presentation and introduction really onto Norbit systems here. So just to give you a bit of a background to myself, I started off as a port surveyor down on the south coast of the UK, and then worked for another multi-beam manufacturer, doing installations, training, that kind of stuff. And then I spent the last 5 years at Subsea 7. Like everyone in the industry, I think, has to have a short spell at Subsea 7, I think, at some point. And then the last month, so a pretty short time now, I've been at Norbit. So back into the pure multi-beam world. So yeah, thank you for NOSP for inviting us here today. I want to give you, like I said, just a bit of a introduction into Norbit, and then talk about our multi-beam offerings, and then phrase it all around kind of the theme of autonomous vehicles, looking at maybe some of the advantages and the challenges that these type of vehicles pose, and then talk about how we're gonna how we set up a multi-beam system. What do we need for a multi-beam survey, and then we'll look at how the autonomous vehicles have kind of developed the Norbit offering in terms of what we do. And also, no presentation, multi-beam presentation will be worth its salt if I didn't show you lots of beautiful images. So I'll look forward to all the oohing and ahhing from the audience as we're going along. And then if we have time and I don't mumble on too long or show you the pictures lots of times, then I want to have a look at some of the SDX functionality that we've got in some of our sonars, and purely because it's cool and I think it's quite a nice application of our system. Okay, so Norbit then. Who are we? Well, we're a Norwegian company based up in Trondheim. We have three kind of segments. We have or departments really. We've got the oceans, which is where you'll find Norbit Subsea,
and then ITS and PIR. So the ITS thing is kind of like a vehicle or asset tracking system. So Odd was mentioning earlier that he has a little tracker in his car that is produced by Norbit, so that's where that comes from. And the PIR side of things are custom product innovation and in-house manufacturing. So that's what those guys do. But the multi-beam side of things, which I want to talk to you about, we're in the oceans side of things here. So yeah, let's go there. Okay, so there's the first beautiful image. So here we have some multi-beam data integrated with LiDAR. I think Rich did a nice job of introducing some of our systems. So some of the concepts that he was talking about earlier have kind of stolen a little bit of my thunder a bit later on, but that's okay. It's nice to hear it from a client as opposed to an employee waffling on at the start here. So here we've got some lovely key walls from our Wbms system integrated with some LiDAR data there. Okay, so what are our products? In essence, we've got two products. We've got the Wbms and the Winghead. So these are the way I like to think about this, or the way I was told about this, is that these are our two main branches of our product tree. So we've got the Wbms and the Winghead, and then underneath here we've got plenty of little branches that kind of cover every application of multi-beams. Each of these systems can be used in any environment because we've got a variety of the system for that. So be it a bathymetry system or a forward-looking sonar, then you've got a Wbms or a Winghead variant. What else do we have? So different frequencies. So we have the standard operating frequency, 200 to 700 kilohertz. And then if you wanted to have a deep water system, then we have 100 kilohertz variety of that. So you can get the extended range with those systems. Also, whether you're going to use the system on an ROV or on a surface vessel and an AUV, there's a variety for that. So, okay, so why the Wbms? Well, it's incredibly compact. Both of these systems are incredibly compact. This is our workhorse. This was the original product that we had with it in our multi-beam range. It's probably the most compact and certainly one of the lightest and most high performance systems out there. It's only about 8.5 kilos in the air, and for the sonar itself, it's only 40 watts power usage, so power consumption. So it's an incredibly high performance, but small and compact system. We'll come on to this a bit later, but it's fully integrated. So we can have a sound velocity sensor and an INS potentially integrated with it, inside it. Again, like I'm going to say, it has an incredible, well, in fact, let's break it down a bit. So this is in, I guess, maybe what you guys would be used to. This is, let's say, the 1 degree system, and this is the half a degree system. So in terms of the beam widths and the nadir, that's how we can break those apart there. We find that a lot of our clients for the Wbms are maybe first-time multi-beam users who are looking for a way to get into multi-beam work. But then we also noticed that with the Wbms, you get a lot of experienced users who are after something that's small, after something that is high performance and low power consumption. Then we've got the Winghead. This is the new system. It was released probably, I think, early last year, so it's not been out for too long, and COVID's kind of interrupted all of that stuff. So this is the real power system that we've got now. We'd say that this is the system that solves our clients' problems. We all know that we've got some really demanding survey specifications coming into the market. So this is the system that's designed to meet and beat those requirements. We'd say that you always say this is, I guess now I'm technically in a sales role, but this is the high resolution system, and then you move on to well what's next? Well, we'll call it the ultra high resolution system then. This is the Winghead when you compare it to the Wbms, but it's still small, and it's still a compact and a low power system. So the applications for it are quite wide ranging from that point. So you'll notice that both of our systems are curved arrays. So you'd say that maybe traditional multi-beam systems have got either have a flat array or a curved array. We utilized curved array technology. And one of the real nice advantages of that is that it gives us much wider coverage. So without having to tilt the head, we can look, I'm going to start waving my arms around a bit now, but we can look up to 180 degrees, up to 210 degrees. So we can look above where the sonar is situated, orientated without having to physically rotate the sonar. Because of the curvature, we have less beam steering than a flat array. So we're able to use split up the sonar into individual sectors so that we don't have to steer the beams to produce the wide coverage we get there. And then because of that lack of beam steering, because we don't need to do it, then there's a much reduced sensitivity to any sound speed errors or variation of the surface there. So that's a nice advantage from that. It's highly portable and conforms well to all vessel types. So it's it's quite hydrodynamic already. So you can have a nice quiet system for that. And then all of our systems have got a sound velocity sensor integrated into the sonar head. You can just about make it out here. This is where the sound velocity sensor goes. So there's no need to have an external sound velocity probe. It's all from that. Oh, and then I forgot to mention on the previous slide that both of the systems have only got one cable. So we have one cable to come up taking all the multi-beam data and the sound velocity. And if you do have an integrated INS in there, then that brings up all the INS data as well. So that's quite a, you see, it sounds almost trivial just having the one cable, but when you're talking about putting these on, small vehicles and stuff like that, and not having to mess around with multiple cables is a real nice advantage of this system. Okay, so this was the system, kind of the big boy really in terms of performance, not in terms of size. This is the Winghead Iats. So this is our latest, greatest system that was released at Oceanology this year. So it's a Winghead variant, 1024 true beams produced by the system and with the 0.5 degree opening angle. It comes with a fully integrated GNSS INS system and is fully motion stabilized. So that's pitch, obviously rolled because that's kind of what you'd expect now, but pitch stabilized in the transmit and yaw stabilized as well. And so that, in terms of this package, is a pretty unique system to the market really. And it's obviously highly portable and can be used on all sorts of vessel types. And still high performance, the big daddy, but it only is 9 kilos with the wet end and the IU. Okay, so that's done my kind of spec sheet review for now. So we'll have a look at some more pretty pictures. So this is an ASV from X-Ocean. And I like this picture because I think it's kind of looking at maybe what the future is for unmanned surveys and renewables. So we're kind of, I think this is where we're all going to be kind of ending up, I think. So I'll try and use autonomous vehicles, to kind of phrase the rest of the presentation and how some of our features have been developed by the use of this. So why autonomous vehicles? Well, they're probably, in essence, the perfect survey platform. They're purpose built and designed around the survey package. So then they're quite rigid. The offsets are generally pretty small because the vehicles are small themselves. They're very quiet. And I guess from a manufacturer and a supplier of multi-beam stuff, it's scalable. You can use them as a force multiplier. So you can throw 3, 4, 5 of them out at a job. And, the productivity from that is going to be pretty incredible. And then the obvious benefits in the reductions in any environmental impact, the reduction in costs, and then probably the main one, there's no people on board. You don't have a massive crew. You're not putting anyone in harm's way or anything like that. Okay. But they do pose some challenges for a multi-beam manufacturer. Firstly, they're generally pretty small, so we need to take that into account. Remote operations, you're looking at, there's no one on board, so how do you control the sonar? How do you control the survey, the the acquisition, that software package. The range, these vehicles want to be out for a long, long time. So the power requirements needs to be, of any system on board, needs to be small. And motion, this is probably the most interesting one for the presentation coming up later on. Anyone who's been on a small vehicle or a small vessel will know that they can bob around like a corkscrew in the water. So that then has an impact upon, the motion can be quite significant, and that has an impact upon your sounding density. So how we're talking about your long track sounding density as we're going along, we've got some very demanding client specifications now. So we need to work out a way to make sure that our sounding density is predictable. We know exactly what we're going to get before we go out. Okay, so Norbit's approach then. So we've got a small footprint. The thing, as I said, is very small, low power, and then we have this tightly integrated INS. I'm going to focus the rest of this on more the surface vessels, vehicles. So that's where the GNSS INS system is obviously going to be applicable. We have a simplified data collection tool, which we call the DCTs, which is the data collection tool. Basically hands-off operation. And then the real cool stuff coming up here is this full motion stabilization for something we like to call predictable density. So you kind of know what you're going to get. I've got some nice slides on that later. And then another cool thing, the dual swath, but we'll come to that in a minute. Okay, so here's just another, I'd like to throw in some nice bits of data here. Okay, so what makes a surface hydrographic system? So here's everything that we need to get it done. You got your laptop or your PC for collecting your data, your multi-beam, positioning system, attitude, and a couple of sound velocity probes, one for the profile and the other for the corrections at the head, and then your software there. And then one thing that in my previous role, another multi-beam manufacturer, which was and also similarly, with ROVs and stuff like that, it's never really the multi-beam that has the problem. It's usually other sensors that are interfaced into it that generally cause those horrendous artifacts you see through your multi-beam data sometimes. So the way that we've approached this here is to kind of try and integrate as much as we can into the multi-beam itself in terms of software and hardware. So here we've got a couple of, these are a bit out of order now. So a couple of INS systems, we've got the Octans, the Planix POS MV and the SPGX blocks on the end there. So just looking at the installation side of things. So this is probably how we used to do things. Just looking at maybe the evolution of a multi-beam setup here. So we've got some examples of some hull mounts here. Then now we looking at the over the pole mount, and you'll notice that what we can do is when we're going from this to this, and we're starting to bring everything, the vessel's now almost not important anymore, because we can now putting everything on the pole. So we've moved from having everything separate to now having everything pretty much together. So we've moved from the hull mount to having everything mounted on the pole, with now maybe putting the IMU inside the sonar with the GNSS antennas on top of the pole. So now your vessel doesn't really matter in terms of that. And here we have a few examples of some USVs. I'm just going to jump through a couple of these. Here's a nice example of a marine robotics vehicle, and then we've got the Wbms stuck on the bottom there. Okay, so in terms of this is the slide I was after. In terms of the INS integration, so we've got our Winghead here. The numbers are our the names that we give to the products. So we've got the Winghead here, and we've added a Planix POS MV, and all that has then integrated into what we refer to here as the I-77, or could even be the I-80S. So all the boards from the Planix top side have gone inside our sonar control system there, and then the IMU is now integrated in the head. So we've taken control basically of, it's all the one cable. Everything's really nice and simple in that. But not only do we take control of the hardware and integrate it that way, but we've also done software as well. So the control software for your POS MV in this case is now integrated inside your inside the Norbit GUI, so inside the control software for the sonar. And also, there's an incredibly handy like wizard that would step you through how to, you know, where do you put your offsets, measure from this bit to this bit, how to do your GAMs. So, like I was saying before, my previous experience is that a lot of the problems we have with multi-beam setups are because the auxiliary systems are not correct. Whereas here, we almost kind of try and take control of that and make it as easy as possible for the user to be able to do that. So that's the whole tightly integrated side of the INS. Hardware and software is done, and I mentioned previously that we have the sound velocity sensor integrated directly into the sonar. So then, like I was saying, just the one cable bringing up your INS data, your sound velocity data, and your multi-beam data as well, which is pretty cool in itself. Okay, so the Norbit solution then. This is basically a complete survey system in here. In an airline checked luggage case, and I can verify that you can check that on an airline. This was my very first day. Well, this picture wasn't, but my very first day at Norbit, I hand carried one of these systems, so you can check them into an airline. So, what's inside the box then? So we've got our multi-beam, our winghead here. This box also contains the LiDAR. So there's the LiDAR system that Rich was talking about in a previous presentation. GNSS antennas. There's all our cabling, so just the one cable, the one wet end cable, and there's a couple of GNSS antenna cables in there too. Here's the SIU box. That contains sends the power to the sonar, and also the POSNV control boards are in there too. And then we've also got the sound velocity probe on there as well. So we cram all of that into one, into one box. So there's your entire survey solution in the one box right there. Okay, the DCT, this is our survey data acquisition utility. This is designed to really simplify any standard survey operations. So this collects takes all the data from the POSNV, takes all the multi-beam data, interfaces that all together, corrects it all, and then it's basically a logger at that point. So you can, it loads the standard S7K files, which can be loaded into any post-processing package, and you get a nice graphical lawn DTM map there. So yeah, but then one of the nice things behind this is that it's all web-based. So this can be run on your iPad or on any platform that you can connect to the network via. So that's a pretty cool functionality there. Okay, so on to some more pretty pictures here. Not only do we do multi-beam bathymetry, but there's also backscatter as well. You can, as you would expect from a high-performance system. Okay, so on to a bit more about the active stabilization. So I imagine all of you are aware of roll stabilization. So if I'm just going to start waving my arms around a bit now. So if the vehicle rolls 10 degrees this way, then we tell the sonar to look 10 degrees the other way, thus flattening out the swath, so we get a nice even swath width like that. Where it starts to get cool now is we started to talk about pitch stabilization. So if the sonar, the vehicle pitches up 5 degrees, then we can tell the transmit portion to actually ping 5 degrees behind. So we're still pinging down. So that's pretty cool as well. Where it gets really, really cool is in the yaw stabilization. So now, and this is really applicable for small vehicles where you're going to get that kind of wandering of the unintentional heading changes with you're on the waves and stuff, and you're just starting to bob around a little bit like this. And then what happens here is, I'll just step to the side so you can see what I'm doing, that then you start to yaw like this, and the vessel's going around like this, so then you're obviously moving in this direction. So then you get these higher density sections here and here, or higher density areas here, but conversely from that, you get these areas out here where you're not getting the same along track density. So now potentially in those areas, you're not meeting your client specifications. And as we all know, the clients are asking for more and more hits per cell as we're going along. So I've got a nice little video coming up to show you how this works. So here you can see this is without the yaw stabilization on. You can see these high and low density sections here. Obviously, this is where we turn it on, and you can see now that then we've got this lovely smooth sounding density. So a predictable sounding density. You know what you're going to get as you're going because we're now fully motion compensated from that. Okay, so why is the full stabilization valuable? Well, we can have this secure target detection. So you know now that we're going to get the uniform data distribution. So we're going to get pings where we think, or soundings where we think we're going to get soundings. So when we're doing our plans, we know that irrespective of where we potentially hit targets, you know you're going to get, I'll fire this one off. There we go. So we know we're going to get the hits on any target across our entire swath. We know that we're going to get enough hits per cell. We can plan for fewer survey run lines because we now don't need to have that contingency in place because we know exactly what we're going to get. And then also we're able to hit this these demanding client specifications where we can know that we're going to meet the number of soundings per meter squared or whatever the cell size is that's been required. Played then. Okay, I like this image mainly because I don't think I've ever really seen wing mirrors in multi-beam data before. It's a pretty cool image. This is from our IATS Oceanology. These are probably the most surveyed cars in the world. You know, in the just outside the in the docks, just outside the Excel Arena down in London. I think every manufacturer's hit these maybe 100 times. I love this image. It's a pretty cool image. Okay, and then just to finish off, I want to briefly mention dual swath. So dual swath is where we're able to have we transmit multiple pings. So in essence, in layman's terms, this doubles your sounding density because we basically have two swaths in the water at the same time. So as we're basically, in essence, doubling our long track density. So the nice effect of that is that, well, we're doubling the long track density. Then potentially because of that, if we're hitting our requirement at that point, we can then double our survey speed. So this is a really nice functionality that will, in essence, either make sure we can hit we'll make sure we can hit these requirements, or we can survey faster. You know, which survey faster, take less time. Everyone's a winner. Okay, just to rattle through a bit more here. Some more multi-beam data. Cool. Okay, I'll do this very quickly so I can see I'm butting up the time here. This is the stuff I find really cool. This is an interesting application of our steerable transmitter. So instead of, it's really how we do, it's how we do our pitch stabilization too. But what we're able to do here is we're not just pinging directly beneath the multi-beam, but we're able to now scan. So we ping at 10 degrees forward and then ping 9 all the way along. So instead of just having one ping in this direction, you're then getting this scanning sector as you're going along, which is pretty cool in a way. And what that means is that, for example, we're almost able to see behind things because we're now not just pinging directly against it. So in this case here, we're pinging from this point, and we're not able to see behind this pillar. But if you remember how the thing looked in this way, you see how it's kind of got this little curvature to it. So that means you can almost kind of see behind walls and stuff now. So we can now fill the gaps in behind the structures here. So this is I think almost a underappreciated functionality that we've had in our systems for quite a while now. And this is scanning mode. So one of the last things then before we've just got some pretty pictures left. This is this STX node, but mounted on a vehicle that is now looking forward. So I've got essentially three systems on here. We've got our multi-beam mounted normally, and then we've also got the LiDAR data, but we've got this STX system looking forward and now scanning as we go. So almost it's like it's now seeing in front of it. So we're almost using it as a object avoidance system, because we're now getting bathymetry scanning out in front of the out in front of the vehicle. Yeah, I think this is a cool way to visualize this kind of thing. Okay, final few pretty pictures. I've got a lovely video coming up of a wreck off the, so you can keep oohing and ahhing as we're going through here. Here we go. I love this one. It's a bit jumpy. It looks better on this screen. Yes, this is the wreck off Oban in the west coast of Scotland. But it's just the level of detail we're getting with the system is just fantastic. So lovely.
The depth on this one is.
I think it's about 20 to 30 meters, something like that. Yes, this was from a surface vessel.
Yeah, I understand.
And then the editing, well, the editing was done in, I think in Quincy, but then this kind of, this is all produced in Cloud Compare.
And what is the depth range of the H80? Still like 160, 70, 80?
Yeah, because it's the same. Yeah, there is for that system, yes, because it's 200 to 700 kilohertz, but optimal is 400 kilohertz. So you'd be looking at 120 meters, something like that. Yeah, yeah. And then there is a 100 kilohertz variety of that with a different product.
Then you're talking about another unit.
Yeah. Yes. Yeah. Yeah. Okay. And then the last few pretty pictures. I love it with the multi-beam data combined with the laser scanner stuff. It just really looks great, doesn't it? Okay. Any other questions? Yeah.
Is there any downside of for the motion compensation? I mean, I'd be curious when you show, for example, the DTM of with the roll compensated or not. I'd be curious to check both. I mean, is there any motion or sound velocity residual? Do they affect more the pings which are compensated for motion, for instance, or it's been negligible?
It's a good question. That's not one I've really thought about before, because I think the benefits are massive, especially with the roll compensation, because you saw that one that then in terms of your survey coverage, you're massively reducing it or increasing your overlap that you require. I guess that you would, if you're steering a little bit more, so then maybe a different, less, because you do have a degradation of your beam widths if you go out, maybe then you're using that. But with a curved array, you're not really affected the same way as with a flat array, so probably not. Yeah, but I think the benefits of motion stabilization far outweigh any potential issues like that.
Quite impressive how many sensors you've been able to squeeze into this unit.
It's impressive, isn't it? Yeah.
All you need to do is talk to Gary now and include the electromagnetic.
Yeah, and then we've got a full.
Chat is complete.
Yeah, exactly. Yeah, yeah, and I think from an operator's point of view, just having the one cable is pretty useful, right? You haven't got to mess around with you'd sync them. If you had cables for all of that, you'd sync your vehicle with the size some of these are.
Are you able to load the water column data as well?
Yeah.
And you mentioned the coverage is like from 180 to 210. And I can see it.
Yeah, 210 being the maximum. Yeah.
I can see the benefit of that, of course, in narrow fjord and stuff. But,
Mhm.
but in our flat sea, I guess even with the winghead, you're still pushing the global physics.
Yeah, of course. Yeah, you would need to. For general survey work, you would narrow it down to 140, 150. Maybe you could probably push a little higher because you have, because of the curvature, you could probably go a little bit higher than you would with a flat array. But physics is still it's still the problem, right?
The footprint is still, that working will be better footprint than compared to a flat.
Yeah, because the deck, but just because of the size of the aperture that available in those outer beams. Yeah.
Is it highly used on? Is there a man using it for our remote?
There are a few. We certainly have been. Our main users are not ROV based, but we have a rapidly increasing number that are. We're seeing the Wbms. We've got lots of clients now starting to use that, mainly because of its size, right? And the power requirement is particularly low. And in terms of integration, it's pretty straightforward to use.
Of course, you don't use any integration of any INS or something.
No, not for subsea. No. But that would be cool. But I think the INSs are too. The subsea INSs are starting to get a bit big, right, to integrate it. And then you're starting to talk about DVLs, and you don't want your DVL next to your multi-beam, right, because they're both shouting away at each other, and you're starting to get a bit of interference there. So it's probably maybe better to keep them slightly separate for now, for sure.
And depth rating on the units itself is that you have
there's a flavor for whatever you want. Yeah, we have a full depth rating on all of them. Yeah. So I think by standard WBMS deep, I think, is that product, and that's 900 meters, but can be 4,000, can be 6,000. So whatever you want, and the same for the winghead. It's all the way down. So where you look on our website, and this was the first thing that took me off surprise, and you go, oh, there's like 30 products, right? But in essence, there's 2. But then any flavor that you want, however you want to use it, there's a product for that. Right? Yeah. But all based on the winghead or the WBMS. Yeah.
Do you supply any brackets, installation brackets for the thermal?
Yep. Yeah. So there are isolation brackets in the box. Okay.
Yeah. You can sign the contracts afterwards.
I'm technically sales now, so I can do any quotes you want. No problem. Yeah.
Thank you very much, Tom.
Okay.
Interesting.
Thanks very much. Thank you.
That was the end of the day, and our say in the previous presentation, one of the next event will be the RTS day. Tor, do you want to say something about that day up here now?
Yeah.
You have the opportunity. Just come. Yeah.
We will bring it even further from last year to the
Yeah.
next level, including more people. I think the way we did it last year, we even having like an online session, was a good way. And we're going to work further on that.
Yeah.
To include more people around the globe.
So still the 1st September.
Yeah.
Yeah. And the house band is
The husband is ready.
good.
The catering is ready. So, yes.
Yeah, I look forward to that.
So
Absolutely.
as long as you are ready, we are ready.
We'll be there. Good. I say we're closing down here now, but there is a bar still there. But also, there's a bar downstairs if you want to hang around for more fancy drinks on the Thursday. So I say thanks for now, and goodbye to the audience listening into this, and see you next time.